Hello world, this is Team Dry Run and I'm Corey.
And I'm Jubem.
I'm Israel.
And I'm Jacob.
And we selected the paper, an efficient variant of the RSA cryptosystem by Cesar Allison. And it's from the Institute of Mathematics and Statistics at the University of Sao Paulo. The reason for this paper was the decryption process resulted in it being much faster with the new implemented algorithm that they discovered. And here is the original RSA cryptosystem and the algorithm that was used originally. And down below that, even farther, we have the M prime RSA, which is the one that we implemented, which increases the efficiency and speed of the decryption. And instead of using the two primes P and Q, it consists of multiple K primes.
Okay.
Page 2 scroll.
We're gonna go ahead and run our RSA old algorithm, and so it tells us to enter two numbers that are prime, and okay. So it's going to ask us to enter number E, which E is a number such that the GCD of E and phi n are 1, and 13 is that number, and phi n is going to be our A minus 1 times B minus 1, and our n is going to be our A times B, as you can see from the steps. So our D is going to be a number that we get from a extended Euclidean algorithm, and here is the formula for it. And our E, which helps us to encrypt our message, is used to get the ciphertext of the message. So when we enter a message that we want to encrypt, so it gives you back the message, and that's our old RSA. So Jacob is going to present the improved algorithm.
All right, so the M prime RSA that we implemented is pretty similar as far as encryption goes to the old RSA. Let me pull that up here. So it's pretty similar. The differences lie in decryption and the fact that Q and P, you don't just have two primes Q and P, you actually have a list of them. And so we're going to use 3, but you can use pretty much any number of them. So we'll go over here and look at this here. So I'm going to use 3. I'm going to use 3, 5, 7, and then I'm going to tell it that I'm done entering numbers with a 0. And so now we get an n of 105 and a phi n of 48. So n is pretty similar, and n and phi n are pretty similar. N is just 3 times 5 times 7, and phi n is 3 minus 1 times 5 minus 1 times 7 minus 1, pretty similar to old RSA. Getting your E is exactly the same as the old RSA. Same implementation, pretty much the same implementation. So now we have, using that value, we find our E and our D. This is where it gets a little bit different with the M prime RSA. So we can see over here that our public key is calculated with N and the E value, which is the same as before, but our private key is actually N and D1 through D sub K, where K is the number of primes that you used up here. So we're going to have 3. And these D values are calculated, shown right here. D sub I equals D mod P sub I minus 1, where P sub I is, so P sub 3 is the 7. It's just the prime, one of the prime that you used, one of the primes that you used. Encryption is the exact same as with old RSA, but decryption is different. It gets a little bit convoluted here, but basically you get a bunch of M sub i's using C, D sub I, and modular of P sub I, and then you apply Chinese remainder theorem to these to get your final message. So if we use a character, we'll use R. We input R, and you see turns it into ciphertext, gives our a list of E's which are used in the decryption process, and then we get our decrypted messages R. So the code for this is a little bit annoying because we had to use a bunch of different vectors, but basically the encryption and decryption over here. Encryption was pretty easy. We just did, since we're only doing one character, we just do our own power function because we were having problems with overflow. We do our own power function on the message and key the encryption modular n, and then we push or we find those m sub i's here, and then we create e's which help us get our final m, and then we calculate our final m and print our decrypted variable.
All right. So, like Jacob just mentioned, we did run into some problems and having to do extremely large arithmetic on integers. So we had to come up with custom methods and algorithms to handle those cases. One of the ones he showcased us earlier right now was the solve for m method. So this method is the one that uses the Chinese remainder theorem. As you can see, our input for our m prime algorithm could be any number of n's, but due to the complexity of this, we had to restrict it to about 3, and we were able to come up with a formula to be able to solve our Chinese remainder for us. And this Chinese remainder theorem also depends on using the extended Euclidean algorithm to find the mod inverse, and this is where this another function we had to implement came in handy also. One more function that we had to deal with was to do with when we are doing the modulo of an extremely large number. Like in this case here, if we have 10 to the 100 mod 297, it would be hard to store that in an integer, so we had to use another custom algorithm to handle that scenario, and this is similar to some of the techniques that we've learned in class on how to handle this. And this is the end of our presentation. I hope that tomorrow I'll see more people using the M prime implementation. And if you have any questions, feel free to ask us. And thanks. And that's it. Bye bye.